All right, so the final session of the day, again on effects of the city, we'll get started with Arpit Gupta, who will be telling us about converting brown offices into green apartments.
Great, thank you so much for the kind introduction. Thanks so much for having our paper on the program. This work is joint with Candy Martinez, who's a PhD student at Columbia, and Stijn Nieuwerburgh, also at Columbia. And our paper is also a little different from others on the program because this is a normative paper as well as a positive one in that we are advocating for more conversion activity as well as describing the conditions under which it can be realized. And this paper is actually going to be out in the next few weeks through the Templeton project at the Brookings Institute. So it's sort of explicitly commissioned and produced as a policy-oriented piece. Let me give you a little bit of the background for why we're studying this question. This is drawn from our earlier work, which we had presented here last year. So this is drawing from Scoop data on back to work plan. So it's updating a little bit the specification we had earlier, and it's just sort of showing office demand at the firm level connected to firm level choices in remote work. And it's not surprising that the firm is going to be in the office most days of the week. Their office demand doesn't change that much. It's not that surprising if you're going fully remote, you get rid of your office. Maybe more surprising is in between. So even hybrid work, which is a very dominant form of work as we know in the hybrid and the remote work era, entails some loss of office space demand. And so we think this is really hitting the office market. So just this morning, for example, I was looking at the office delinquency statistics. So office loans are very quickly going more delinquent at a pretty steep pace. So as of today, they're about 5.6% of office loans are delinquent. That was, last year it would have been less than 2%. So there's been a big increase in defaults on these loans. And here we just sort of see that whether we look at industry, whether we look at cities, places that have more remote work exhibit lower office demand. So we're seeing these trends in office use play out as a function of how remote places are in ways that imply that office demand will therefore be down substantially in a lot of cities. So here in San Francisco, for example, we're now at like a 33.9% office vacancy rate. So it's like 1 in 3 square feet of office space is vacant in downtown San Francisco. All right, so that was all kind of earlier work which had established the doom and gloom of office. And so for a change, we decided to be constructive about the problem and think about, first let me dwell on the doom and gloom for a bit. So we've got this lower demand for office coming from remote work. We've got lower valuations on these buildings coming from the demand shock, also coming from higher interest rates, which is a big effect, of course. These trends have really big implications for cities, which draw a lot of their revenues from these buildings. At the same time, there's not enough housing, so we've got affordable housing shortage. And then finally, we also have a climate crisis going on. So in New York City alone, buildings are actually responsible for 70% of the carbon emissions in New York City. So we've got this stranded asset problem in multiple dimensions. These assets are stranded because there's less demand for them, and also because they're polluting. In New York City specifically, we have a carbon tax that's coming in, which will mean steadily increasing carbon taxes for these buildings. All of these mean the assets are less valuable, less usable for their originally intended purpose, and raises the question of what we're going to do with all this space. So our proposal is to turn the offices, particularly turn the dirty brown offices that are environmentally polluting, into clean multifamily buildings. And to do so, we're going to do 3 things. First, we're going to identify whether this is physically possible or not. Then we're going to analyze whether it's financially feasible to do. And then we're going to explicitly analyze the policy levers at the local and state and federal levels, which can accelerate this conversion activity so more of it happens. So this is basically the feasibility part of it. And this is across the country where we've identified candidates for conversion from dirty offices to green apartments. I'll go through the criteria that go into this, but it's basically here just to illustrate, I think there's a lot of scope across the country to convert office buildings all over the nation. So not just San Francisco, New York, but also possibly other cities as well. Here's what it looks like just in New York City. So on the bottom there in the financial district, we've actually been converting buildings for several decades. And we've had even local public policy programs intended to encourage the conversion of those office buildings. They have a particular typology that actually makes them very suitable for conversion into multifamily. But you can see from the dots here, we think there's still some more room for conversions in that sort of downtown financial district area, as well as in Midtown, particularly East Midtown, as a lot of these very low value office properties that would be suitable for conversion to multifamily. Okay, so let's first identify these candidates. So just a little bit of descriptive statistics here. So in New York City, we're actually getting through Local Law 97 a new carbon tax. So this is going to impose steadily increasing fines. So in 2024, 2030, we're going to get more fines on buildings that violate emission standards. And so these are envisioned or coming in many different cities across the United States. Some exist internationally. And here, the point is just the distribution of these fines is heavily concentrated in these older buildings, these sort of pre-war buildings. And so these are also the buildings that we know from our prior work, at least in demand due to remote work shock. So that kind of works out. You've got this kind of concentrated cluster of buildings that are both dirty and people don't want to be in them. So let's figure out what else to do with that space. So how do we identify a plausible candidate for conversion to multifamily building? Well, we're going to take some of these commercial districts, so here like Midtown, downtown Manhattan, where we think that the policy imperative from an externality standpoint is the largest, right? So we just saw earlier that we think that commuting kind of brings a lot of externalities in terms of crime, in terms of consumption. Therefore, the vacancy problem in these downtown areas is the strongest, and hence there's the strongest public rationale for doing something with the space. We're taking older buildings. Benchmark here is before 1990, but we have a whole sort of decade of construction analysis. We kind of exclude the highest quality buildings because those kind of seem to be holding up. We're taking minimum 25,000 square feet. The big requirement, really the big requirement here is the floor plate. So the floor plate is the dimensions of the building. And when this floor plate dimension gets really large, it makes the economics of conversion a lot harder. You essentially either have to then dig a core through the center of the building or down the side in order to release more surface area so you can have all the bedrooms adjacent to the corridor. And so we kind of impose a requirement you can't have a distance that's too far from the core of the building to the window. That kind of also means we're picking up more of those very old skyscrapers that have already a narrow floor plate. We also want to pick buildings that don't have too much of a tenant population in place. So buildings where you don't have too many existing tenants. Actually, we've seen some cases where actually the existing tenants want to leave, and so they actually pay you to get out of the lease. But in general, we're going to assume that if you have a lot of tenants, it's going to be hard. So we're going to focus on buildings that are more vacant. And then finally, we're looking at brown offices. So we're looking at buildings which violate New York City's emissions standard for our benchmark. Of course, there's going to be more conversion possibilities if you don't require that. And we're going to be focusing on conversion because it's also a lot better from an environmental standpoint, taking into account the embodied carbon in these buildings. So if you tear down the whole building, of course, there will be other tear downs as well. You basically have a lot of carbon, the steel, the concrete in the building that you're getting rid of, and you have to kind of build that all from scratch. You save a lot of environmental benefits if you do it through the conversion route. All right, so this is what we get. So on the far left is what we observe in New York City. So we're kind of starting with a total number of buildings at the top. We're steadily employing these different requirements for what counts as a possible candidate for conversion. And so we think we can produce basically 38,000 apartment buildings in New York City with buildings that we've identified as possible conversion candidates. What we then do is kind of employ a similar algorithm for the United States. So the difference between New York and the whole nation is we have better emissions data in particular in New York. So we use the emissions data that we have in New York to kind of fit a model for what is a likely brown building, and we employ that national model out for the whole country. So that adds up to over 100,000 apartments, which would save sort of 500,000 tons of CO2. This again is the graph of all those buildings. And this can be scaled up given we have sort of incomplete data coverage in CompStack, which is our data provider for this. So if you kind of count for the fact that we don't observe all buildings in our sample, we think that this is representative of about 400,000 new apartment buildings that are plausible candidates for conversion, given our algorithm. So to put that into context, new apartment deliveries in a typical year is 260,000 new units. So if we converted all of these at once, it would be a large multiple of the existing number of buildings, and it would replace a pretty substantial amount of carbon as well if we're simultaneously remediating the carbon expenses of these buildings while we go through that conversion process. So typically the carbon, emitted by buildings is coming from the boiler, the heating system, things like that. And, as you're doing the conversion, you can kind of replace a lot of those electrical, heating, cooling, et cetera, systems as you go. One challenge is I'll come back to is this loss factor. You're not getting as much space as a apartment building as you are with the office. Okay, so that's just from a physical feasibility standpoint. Just can the building physically be transformed into a multifamily building? That doesn't mean it pencils out financially. And so that means the next step of our analysis. And so what we're actually going to do here is a pro forma real estate analysis where we put in a lot of assumptions about how the building is going to be in the pre-conversion state as it's an office, take into account all the headwinds we talked about. We're going to compare that to what we think are plausible financials for the building if we convert it to figure out whether this whole thing pencils out, whether it makes financial sense to convert the building in this way. And this is going to be one of the main public goods we hope to release as a part of this project. This is all going into a calculator, which will be on a website through the Brookings Institute. And the idea is any developer can type in whatever parameters they like about a particular building to see whether conversion makes sense for them. A local policymaker can use this tool as well to figure out, is there a shortfall in the conversion not penciling out financially? If so, what would therefore be the required subsidy necessary to make the project NPV feasible, right? So this is all not just a set of results, but a framework to think about the conversion potential. And so we just kind of throw in a variety of assumptions here. Again, these are all controllable with dials in our eventual calculator, which basically get at what's happening with buildings before COVID, after COVID, et cetera. Okay, so there are a variety of things that are going on here. We're basically putting together a financial model that takes into account the higher interest rate. It just got a little bit higher last week. We were taking into account the remote work impact here, which is impacting the rents that you can collect if it's an office building. And so we think that the higher interest rates, the remote work, these are all impacting the property value of the building, and then finally the climate part of it. So taking all that into consideration, the interest rates, the remote work, the climate taxes coming in, we think there's about a 60% financial loss for buildings. Here, this is benchmarked all in New York City, but so here's some numbers across the whole country. Okay, so the idea is that if you take these shocks seriously, you think the building should be worth a lot less than it currently is. Can you then, as a developer, buy the building at the new valuation, spend the money to convert it into an apartment building, and that's expensive, and then turn this into a green apartment building? If so, will the resulting cash flow stream make this project NPV positive, right, and financially worthwhile for development purposes? And so we also put in, assumptions here about what the rent is going to be, what the financing cost is, so on and so forth. These are all, both assumptions that we kind of do our best guess at, but also toggleable dials again in this financial calculator. So the upshot is basically it can pencil out, but this is, I would argue, actually a little bit of a knife edge case. So we're getting like a little bit of NPV here. So this is a building that was about $100 million in valuation, just like a standard kind of assumption here. We think the NPV of conversion for this sort of standard building is about $4 million. The reason I argue this is actually a little bit of a knife edge case is because in order for this value drop to happen, you're going to have to realize a pretty large financial loss. So that may require a foreclosure or default event for this building to actually realize that loss. And then developer has to go through it. They're going to have to go through all this expense. And at the end of it, they're getting $4 million in NPV, 17% IRR. So it kind of makes sense for them, but it's a little bit dicey. So it suggests that conversion can just pencil out, assuming the large value decline. And the reason it doesn't pencil out even more easily is office rents are actually pretty high relative to apartment rents. So you basically need to write down the value of the office a lot and then convert it into a luxury apartment in order for this thing to even be close to working out. All right, so if you tell a policymaker this, the first thing they're going to tell you is, okay, well, that's going to generate luxury units, but we don't want luxury units. We want affordable housing units. Okay, so we consider affordable housing mandate. What if you then require the building owner to provide affordable housing, affordable as in requiring that the rents on the unit not exceed the local area median income. So it's a very common requirement through exclusionary zoning and other mandates recently. So we basically conclude it doesn't really pencil out if you do that. You kind of really need to have these units be either market rate or have the government provide more subsidies if they want these units to be affordable housing. And we have an estimate of exactly how much. So in order for that to happen, you can do a few things. You need property tax abatement. So that's basically a program that would allow for the government to cut your property taxes if you generate affordable housing units. That's actually something New York City did through the 421G program, specifically for office conversions back in the 90s. It's something New York City used to do with the 421A program. It's something many other cities have done in various contexts. You could also subsidize the debt that's going on here. So part of the problem here is how expensive the interest rate environment is. The government can subsidize that. And finally, you have the Inflation Reduction Act. And we're going to highlight some provisions in the Federal Inflation Reduction Act, which we think can cover the cost of these conversions, provided they also meet that environmental perspective. So part of the point here is that this conversion is something that policymakers should be really thinking about because they get more tax revenue this way if it happens, right? If the value of the office goes down, you lose all that revenue. If you can convert it to higher use, you kind of get more property tax revenue across a lot of different scenarios. We do a lot of other sensitivity analysis, how sensitive are these results to conversion costs, rents, all that stuff. Not surprisingly, the results are very sensitive to all the inputs and assumptions going into it. And so we think of this whole analysis as less a definite indication that these buildings definitely should be converted and more a kind of proof of concept that conversion can pencil out under the following assumptions. It would affect, however many units, and policymakers that really want to push this need to think seriously about the types of incentives necessary to really make it happen. So that's going to be the last part. What policy levers really need to happen? So this is a very active and ongoing discussion in many cities. Basically, you need to change the zoning and building codes to make it happen in the first place. Ensure that the building owner can do this conversion as of right, to avoid all the delays and construction costs, lawsuits, and so forth that derail these kinds of construction programs in general. You need to change building standards to be more flexible in allowing conversions, particularly with this bedroom issue. So Charlie Munger, right, loves these windowless dorms. That's sort of one way to get these conversions to pencil out is remove the requirement that every bedroom have a window, and providing, additional density bonuses, getting rid of parking requirements, these things like that. Cities are actually moving already in this direction. So like in New York, Eric Adams just announced a big new zoning overhaul that also gets rid of the parking requirements, allows for SROs, and is also moving forward on the office conversion side. Last thing I want to emphasize is Inflation Reduction Act has a lot of money that's being spent, and we've identified a number of provisions which basically are large pots of money which can go towards this purpose because these are funding sources intended for different spending sources that are energy efficient. If you take a dirty office building, fix the environmental issues, it qualifies for these subsidy programs. And so we think that there's a lot of money out there which can, from the federal source, which can also go and augment the local policy stimulus in order to make more of these happen. All right, so that was all our paper on conversions. I do want to spend the last couple of minutes and just pitch another paper, which is a work in progress. So here we're measuring the productivity impact of remote work from GitHub data. So looking at commits, coding data commits, and here the comparison is that the two lines at the top there are basically fully remote and hybrid work. And the bottom line is the in-person workers. And this is comparison of how many inputs you're doing on GitHub compared to before the pandemic as a proxy for productivity, right? And so we see two things. One, we see greater dispersion. So remote workers are doing more things at all hours of the day. So we know that from earlier work. And we also see a big increase in this productivity measure for the fully remote and for the hybrid workers. So it's consistent with a substantially positive impact of remote work on productivity. Here, let's go back to Brian's point earlier about scaling, firm scaling. So here we're measuring basically employment counts for firms, and this is looking at a coefficient of whether your firm goes more remote. So the remote firms basically scale a lot more when they go remote. And it's coming after sort of flat pre-trends before the pandemic. Their kind of employee count sort of rises. So this is very much work in progress, but I figured I'd use the opportunity to pitch it to you a little bit and try to solicit more feedback from you on where we should kind of take this project forward. Thank you all very much.
So can I ask the first question? I had the following thought experiment in mind, which is if the alternative to converting these buildings is basically tearing them down and building something entirely new, the carbon benefits are potentially much bigger because steel and concrete production is so carbon intensive. So I was wondering if you'd considered that, or if there's some way to quantify that in a way that might be useful to policymakers.
Yeah, so there's some existing work that quantifies this embodied carbon problem. So how much carbon is existing in structures. So, it'll be common for buildings to have tons of embodied carbon. It just varies so much by existing buildings. So that, for sure, that's in the background. It's for us, that's just sort of the reason why we focus on conversion from the get-go as a way of trying to remediate the emissions. But I take your point. We can probably think a little bit more about doing a more like-for-like comparison and really quantifying what the total carbon benefit is relative to tear down.
There's another carbon benefit to assess, which is it worthwhile to go from brown offices to green apartments? Or would it make more sense from an economic perspective to go from brown offices to brown apartments? Okay, so you position this paper as about going from brown to green, but you told us nothing about whether there's actually what the economic payoff is, or what the carbon reduction payoff is from the brown to green conversion. I have no idea. It may be that these things that are marginally, pencil out to a positive NPV conversion might be a lot more attractive if they didn't have to go to green. They just went from brown to brown. And you still avoid the tear down.
So that's the emissions line there. So that's basically the tons of carbon that we save if we go ahead with a conversion.
Okay, but what's the cost side of that? If we went from brown to brown, we still don't have to tear down the buildings. That's Jose's point. But does it make the conversion a lot cheaper? How much of this conversion cost is really?
Most of the conversion cost is not coming from the carbon remediation.
Okay,
right?
well then that point should be drawn out. That seems like a key point to draw out. And maybe it's in the paper, but I didn't get it in the presentation.
That's a good point.
So I'm hearing a lot from policymakers in the UK and also in Canada about things like this, but nobody seems to be pulling the trigger on it too much. Now, one of the main reasons for doing these conversions is actually because there's a social value to having a lively city center. Would there be any way to estimate, say, the multiplier effects that just come from housing more people in city centers?
That's a great point. Something we've thought about. I think it would be possible to do that, especially with historic conversions that have happened. For example, in like downtown Manhattan, what the multiplier was. I think we didn't feel we had like a good enough identification strategy to really kind of sell that. One other point to mention just about other countries that are doing it. So one thing I learned over the course of this project is in the Netherlands, they actually have like a central government office dedicated to this. It's like a team of people that go out and help people convert their buildings. And 15% of the housing constructed in the Netherlands over the last like 10 years comes from office conversions. So there are other international examples actually of policymakers in countries that have done this very successfully.
I was wondering if you've thought about sort of what are the equilibrium counterfactuals. So if these buildings are converted, if they're not converted to residential, then you'd sort of expect the office rents to fall. It's possible that there are suburban locations where residential construction would take place, except for the office demand that's happening now. Or maybe you think the buildings will stay vacant. I'm just sort of thinking in a sort of from the perspective of a broader urban equilibrium, what do we expect the spillovers to be to the suburbs, to the size of the office market in general, since I think that'll help understand what the net effects will be on carbon reduction and so on.
That's really part of the motivation here. So what we're identifying is basically like 10 to 15% of office buildings are financially feasible, or sorry, are physically feasible, of which about half of those are financially feasible for conversion. So it's definitely not most office buildings by any stretch of the imagination, but what, think of a market like New York is like in the low 20s in terms of vacancy rates, or a market like here that's in San Francisco that's like 33% vacancy rates, right? If you take an office market like that and you take, let's say, 5% of the office stock and convert that, you've now kind of changed a sort of disastrous office environment to one that moderates substantially. So you can sort of, even with not that much conversion, the hope is you can kind of potentially stabilize a lot of what's going on in the office market. At the same time, you're adding more residential, you're adding more eyes on the street, you're kind of addressing some of the fundamental problems of the downtown and sort of help revive the whole city, even if it's not like a ton of units. So definitely that kind of equilibrium sort of thinking is behind this. We haven't like formalized exactly what it would be, but that would be like a great step to think about.
If I could piggyback on that, interesting laying out of the issues, particularly as somebody looks at these conversion issues. But I was curious how you might get a more dynamic result through phrasing it as equilibrium, because there's an implied assumption here that the current status of remote work is going to continue, and the current status of what is perceived as lack of office demand in urban centers is going to continue. And that is not at all clear, at least looking locally. And sort of the related question to that is, there is some argument that can be made that the reason why we have all sorts of problems, both in the office space area and in the housing area, is because of the imposition of various things that interfere with the private sector response. It sounds to me like you're proposing more interference with the private sector response. Have you looked at what might be a reasonable, this is where it piggybacks off of the earlier question, a reasonable private sector response?
Yeah, so first, just to clarify, a lot of our objective really, it's gone here. Anyway, a lot of our objective really is to remove the zoning, regulatory impediments that are preventing some of these conversions from taking place purely from private developers. So I'm totally in agreement that a lot of the ways that we're going to get this done are by removing government that is currently a blocker in this situation. I also think, back to your first point about are people going to go back to the office, this is actually a great way to get people back to the office, because we know from work people here that commuting distance, right, is a key barrier behind people getting to the office. And so if you build more apartment units downtown, that will produce a population that is more inclined to come back to the office. I think in terms of is that office oversupply or not? The other thing we know from our earlier work is it's really the newer buildings that are holding up the best. So I think even if office demand kind of comes back incrementally from these new workers, that will result in either new office construction, or it might change like a little bit on the margin, whether you want to be in a building from the 80s or the 70s. We're really focusing on the buildings from like the 30s and the 20s and so on and so forth, where we think this demand has really fallen away.
Hi, a few years ago, a co-author and I published a paper. It was sort of a theory simulation paper analyzing the effect of taxing emissions in cities where the tax is levied on buildings and on automobiles. And so we came across some engineering literature saying that heating and cooling costs from a building and thus emissions depend on the surface area of the building. And that in turn implies that the way to tax buildings is not simply by square footage, but in a different way that I won't tell you about. You can ask me later if you want. But what's the form of this emissions tax? That's my bottom line question.
It's on the emissions. It's on the actual emissions for the building. So they have building level data. How much emissions are you putting off? And so
is that right?
Yeah. And so however it happens, because they have the energy usage, the heating, the cooling, et cetera, et cetera. So they have all that data.
Okay, so it's based on energy usage, not on actually measuring emissions.
That's right.
Okay.
All right. Usage. That's right. I should be clear.
I had a couple of comments, questions. One was when you said vacancy rate, to me, there's a couple of headings. Vacancy meaning it's empty and nobody's there, versus it is currently on a lease and someone has it on the sublease market,
Right.
and it's still also physically empty. There's no humans in there, but it's being paid for. What was What definition were you
It's
using?
sort of like for San Francisco, I think it's like a 33.9 availability rate, including the subleases. I think it's
Okay,
like a
the
high
two together.
20s with an actual vacancy. Yeah.
Okay, thanks. One, two, the conversion to housing as a number, all the financial metrics you ran there seem, did I hear you say it starts with, first you have to realize you're going to lose a lot of money
Yeah.
on the value?
Yeah.
And so the owner of the current building has to have a very quiet conversation with themselves about losing some large amount of money before you can start this whole premise. Is that, did I hear that right?
So that is happening in some cities. San Francisco is
I'm
actually is the best example. Office per square feet have gone from 800 before the pandemic to now you're seeing actual sales at 200 square foot.
Yeah.
So there are certain cities where that process of acceptance, denial, et cetera, is moving along more rapidly.
Okay, thanks. And the other last one is, have you seen anything that's more, here you're talking about housing, are there other uses that you've seen might pencil out better? I'm thinking like community college use or alternate school campus use or things like that.
Yeah, it's outside the scope of this paper, but I absolutely agree with you. And even in, I know in New York, there's been interest by educational institutions, by hospitals. Lab space has been a huge demander of urban space. Everything from warehousing space, asylum centers as well. So there are a variety of uses, I think, that can be done with this space. And like the big picture is like cities are constantly churning in renewal, right? So the space in Manhattan was once factories, is now lofts, is now something else. So this is just part of the general process by which cities turn over.
All right, I think we need to move on. Thanks so much. All right, so second paper of the session is going to be presented by Jack Liebersohn on the short and long run effects of remote work on US housing markets.
Thank you so much for having me. As we've seen from all these sessions and from a lot of research by folks in this room, the rise of remote work has changed how people want to consume their housing. So it's changed where people want to live, the movement towards suburbs, exurbs, and possibly entirely new cities. And it's also changed how much housing people want to consume. People have home offices and during the pandemic, spent more time at home. It led to an increase in the size of homes that people wanted to consume. Now, as any good urban model will tell you, this led to changes in the price of housing, both in relative terms across space and in absolute magnitude. Housing costs went up dramatically during the pandemic and have stayed higher ever since, despite the rise in interest rates. The argument that we're making in this paper is that the long-run implications of remote work for the US housing market are going to look very different than the short-run implications have been. So to give you an example of how that might play out and some of the mechanisms that we're studying here, I'd like you to consider a city like Houston. Historically, Houston has been relatively affordable, has had relatively affordable housing for the middle class. And in part, that's because construction is easier in Houston as compared to places like, say, the Bay Area or the LA metro area where I live. However, during the pandemic, there was a rapid increase in housing costs, rents, and house prices, even in relatively easy to build places like Houston, Dallas, other places in Texas. Now, in the long run, we think that new construction will accommodate some of the changes in demand, even though that new construction didn't happen during the pandemic, simply because construction takes a while. What that's going to mean is that in equilibrium, more people are going to move to Texas because housing will become more affordable. And that'll have effects on the sort of general equilibrium of the housing market in the United States, including places like California, where people are moving from. So those are some of the mechanisms that we're going to study. The basic point is that construction takes a while. And so the short-run equilibrium that happened during the pandemic is not reflective of the long-run equilibrium that we expect in the housing market. So our paper has two parts, and I'm going to take you through each of the parts one by one. In the first part, we're going to take as a given the changes in population movement and the changes in housing costs that occurred during the first years of the pandemic, the rise of remote work. we're going to interpret those changes through the lens of an urban model and use the structure of our model to back out what we think are the fundamental shocks. So what do I mean by the fundamental shocks? I mean the shocks to housing demand to live in each city in the country or each location, and the changing demand for larger homes. So we're going to back out or the change in demand to live in every US county, and also within each county, how much bigger homes did people demand? Then we're going to feed those shocks back into a version of our model that allows for more construction. What do I mean by more construction? Well, we're going to assume that in the short run, new construction was not possible, but in the long run, it is possible. And so when we take those shocks and feed them back into the model, what we arrive at is a different urban equilibrium with a different level of housing affordability in each location and different patterns of where people live. So there are two key facts that we want to feed into our model and that we want to interpret through the lens of our model. The first is the aggregate increase in rents that occurred from 2018 to 2021. So overall, we think that the rise of remote work led people to demand larger homes, both for home offices and because they're spending more time at home, and so they might want to, consume more housing in other ways. The second is the sort of set of cross-sectional facts that house prices changed, or that housing costs changed in relative terms across locations. So one of the big cross-sectional facts that we're interested in interpreting is the donut pattern that we've seen documented in many papers by Nick, by Arpit, by Jan, by other people in the room. With the less need to commute into downtown offices, people were able to move further away from CBDs, and prices in suburbs and exurbs rose relative to housing costs in CBDs. Okay, we microfound a model. It is sort of, if you've seen urban type models, it looks very standard. We log linearized the model, and what I'm going to take through is sort of the 5 key equations that define the urban equilibrium in our model, right? And this is the result of a log linearization. In the model, every individual chooses how much housing to consume, so you can think of how many square feet, and also which location they want to live in. For our empirical application, each location is going to be a county, but in principle, we could have estimated this with zip codes or MSAs or whatever you want. Okay, so the first equation is the housing demand equation. And it says that the amount of housing per capita, so you can think how many square feet, is decreasing in local rents. But then there's also the housing demand shock epsilon. And this epsilon is going to be one of the shocks that we're going to try to back out from the data. And this is specific to each location. So epsilon has a subscript I is a location. The second equation is the housing supply equation that says that the change in total housing in each location is governed by the housing supply curve and a housing supply shock Xi. Each location has a housing supply elasticity, sigma, and ultimately we're going to use ultimately, we're going to assume that in the short run, each location has housing that's supplied completely inelastically. In the long run, the elasticities will be positive. Third equation is the location demand equation. So this says that the change in population in each location is decreasing in local rents with an elasticity mu. There's also a location demand shock, eta. If some places become more attractive because of the feasibility of remote work, the etas will be more positive in those places. Finally, there's an outside option that determines the population in each place, and that's U tilde. U tilde is determined endogenously in the model. Fourth equation says there is a housing adding up constraint, which says that the total amount of housing in each location is the change in population plus the change in housing per capita. And the last equation says that everybody has to live somewhere. So the total population in the US equals the total population in each city summed up. Oops. Okay, there we are. Okay, so those are the 5 linear equations that determine our model and that we solve. Now, I'd like to speak a little bit about the structure of the model and why we picked this model. Compared to some models, it's relatively simple. We only have 3 shocks: a demand shock, a supply shock, and a location shock. The model is not dynamic, although we do a dynamic extension in the paper. And the reason why we like the simplified model is because we can calculate formulas that back out the shocks from observed moments in the data. And we can also calculate analytic formulas that show what the effects on average rents are based on those shocks. And so we can calculate pretty much everything we do analytically, and we think that gives a lot of insight into the structure of the models and how different sort of counterfactuals will affect the urban equilibrium. Okay, so what are the forces that govern average rents in the model? Well, there are 2 important forces. One is the demand for living in particular places. If more people want to live in places where housing is more elastically supplied, that will lower average rents. Why is that? Well, if we take one person and we move them from an inelastic place, like the South Bay, to an elastic place, like Urbana-Champaign, house prices will rise a little bit in Urbana-Champaign because housing is elastically supplied there. House prices will fall a lot in the South Bay because housing is inelastically supplied there. And that means that in equilibrium, the average house price in the US will fall. I should say, I'm saying house price, but it's really a model of rents. House prices are dynamic. And we extend it to that, but I should really be saying rents. So the point is that the location of where people want to live affects the average rents and the average levels of affordability. You can probably see where this is going. If there are some sort of shock, like a remote work shock, that allows more people to live in places with an elastic housing supply, that will lower rents overall in the country. Now, there's another force, which is the demand for housing size. If people demand larger homes, that will mechanically increase rents. If there's a shock, such as a remote work shock, that makes people demand larger homes, then people will consume more housing, and that'll raise housing costs. Ultimately, we're going to see that those forces go in opposite directions, and the exact magnitudes will depend a little bit on the calibration. Okay, so what about the short run? Well, in the short run, we assume that housing is supplied perfectly, inelastically everywhere in the US. And that's how we're going to interpret the years sort of 2019 to 2021. It's a stark assumption, but we think it's relatively reasonable. Not very much housing was constructed then. If we modify it by allowing a little bit of housing to be constructed, it doesn't change anything quantitatively. It just makes our formulas a little bit more complicated. Okay, we think this captures one of the key facts about the pandemic, which is that even in relatively affordable places historically, even in those places, rents rose by a lot. And the sort of best way to explain that is to say it was hard to build new housing there, even though in principle it should be possible. In the long run, the forces will be very different because the shift towards elastic areas will affect aggregate house prices as those elastic areas are able to finally build housing. In both the short and the long run, the increase in demand for larger homes will raise prices. So that force is still there, but that will also be ameliorated in the long run as more homes get built or as larger homes get built. Okay, so now I'm returning to the 5 key equations. I'm just showing you the same equations as I showed you before. The only difference is that the second equation is zeroed out. It says that in the short run, no new housing is constructed. The elasticities are set to exactly 0 everywhere, and there is 0 supply shock. Okay. That's the short run of housing markets. With these five equations, now 4, and a few lines of algebra, we can back out the structural shocks that we care about. The two structural shocks we care about are given on the first line, epsilon, which says how much housing people consume, want to consume a bigger home. The second structural shock, eta, it says how much where people want to live. What you can see is that both of these shocks are linear functions of the changes in population and the changes in housing costs, which we measure as rents, in each location. The exact linear combination of housing costs and population that tell us each shock depend on the calibrated parameters lambda and mu. Lambda and mu are the two elasticities of housing demand: the elasticity to move to a particular place and the elasticity to consume a larger home. So let me, before getting to our estimates and telling you our preferred calibration, I want to give you a little bit more intuition for what those two elasticities are. Okay, so I'm going to start with mu. This is what we call the location demand elasticity. That says if rent is higher in a particular city, how will the elasticity to move there change? So in a Rosen-Roback type model, mu is infinity. What does that mean? That means that if rent goes up in one city compared to an identical city, people will move out until the rents are once again equal. It's a sort of Rosen-Roback assumption. If mu is 0, then people won't move regardless of how high rents are. They don't care about rents, they really want to live there. We think that a high mu is reasonable because we're talking about the long run. We actually have another paper where we try to estimate mu and we come up with large values. It doesn't have to be infinity, but a mu of something like 10 is basically infinity for the quantitative purposes. And again, that's over the very long run. We're thinking maybe 30-year time frame. The second elasticity is lambda. That's the housing demand elasticity. It says how much of a smaller home people will want to consume if rents are higher. If lambda is 0, that means that everybody consumes a unit, just a home. If lambda is 1, that corresponds to Cobb-Douglas housing consumption. We think lambda equals 2/3 is reasonable. That's based on a bunch of previous research other people have done. And it's what we choose in the other paper. But the results are not very sensitive to lambda. They're more sensitive to mu. Okay, so with those calibrated parameters and the formulas I gave you a few slides ago, we can back out the fundamental shocks to housing demand and location demand and how they changed from 2020 to 2022. We use rents data from Zillow, and we use the population data that Nick helpfully provided as a public service to the profession. I guess FOIA'd and USPS provided it with some help. That's right. Now, for the long run, we don't assume that housing is inelastically supplied. We say that the housing supply will instead be equal to its historical levels. And we use the elasticities from Baumsnow and Hahn as our sort of benchmark. And we do some work to reconcile those with the elasticities from SIEPR, which we think can be reconciled if we think about the time frame that they're estimated on. Right. Net change of address requests from USPS tell us population. Okay. So in the paper, we show various maps of where the demand shocks are. Not surprisingly, they look a lot like the maps of population movements and rent changes. So you see exactly the same donut pattern, the same decrease in demand for CBDs, the same increase in demand for sort of suburbs and exurbs. Let me advertise the paper. You should look it up and you can see some nice maps. I'm going to skip those in the presentation in the interest of time. And we plug those back into the model. And as I promised you, we derive formulas for the size of these two effects. So the intuition I gave you a few minutes ago said that if more people demand housing in elastic areas, that will decrease aggregate rents. And in fact, we show that the size of that channel is exactly equal to the negative covariance of the demand shocks and the elasticities. And that's scaled by the sum of the average housing supply and the average intensive margin housing demand. Okay. So the effects aren't as large if the average housing supply is higher everywhere. So as demand shifts towards more elastic areas, the aggregate price will fall. This scatter plot shows the relationship between what we think are rent changes over this time and elasticity. And you can see there's a positive relationship, although it's sort of curved. What this means is that the demand shocks were quite negative in the most inelastic parts of the US, basically CBDs of major coastal cities, right? The demand shocks were more positive in the sort of suburban areas in the middle, and they were roughly flat in very rural areas. This means that there's a positive relationship between elasticities and demand shocks. And what that will mean is that the effect of location demand will be to make housing costs more affordable in the long run, even though that didn't happen in the short run. We calculate that sort of using our benchmark parameters, the covariance is 0.0023. We calculate a sort of average housing elasticity of 0.25. And so the net effect will be a long run, 0.5 percentage point lower price due to remote work relative to the pre-pandemic benchmark. Okay. If you think remote work will change where people want to live by more than we saw because it'll expand, then this estimate can be scaled up accordingly. If you think it'll return to a lower level and the house location demand shocks will decrease, you can scale this down proportionately. The second effect is that people demanded larger homes. And this channel is actually very easy to calculate. It depends on the average housing size demand shock. So the average value of epsilon, and we derive a formula for that. And again, it depends a little bit on what we think of parameters are. For lambda equals 2/3, we arrive at a real rent increase of about 0.045, that is 4.5 percentage points. Keep in mind, that's way down from the short run effect, which was 8 percentage points. Right? In the short run, rents went up by about 8% over this time period. In the long run, we think that'll go down to 4.5%. Right, and sort of, we can calculate something like 4.9 percentage point long run channel. Okay, so the net effect of remote work will be the sum of these two channels. In both cases, these channels mean that in the long run, housing will be more affordable than it was in the short run because new construction gets built to accommodate the changes in housing demand. The fact that people want larger homes will increase rents. The fact that people are willing to live in more elastic areas will decrease rents. We think the net effect is still likely to be positive, but not nearly as positive as it has been. And depending on parameter values, something between 2 and 4 percentage points, down from the 8 percentage point short-term effect we saw. Okay, so there's a lot more in the paper. Implications for prices, evidence that, you know, our results are starting to happen. We wrote this paper we started writing it about a year ago, and some of the things we predicted about sort of long-run population movements are in fact starting to happen, which is really exciting. So I encourage you to look up the paper for more, more detail. And I'm happy to take your questions. That's all I have. Or I'll let whoever controls the microphone.
Thanks. Great. So one really interesting, I don't know if this is part of it, or one claim I heard is that hybrid, as much as remote, is bringing a bunch of land into use that was previously unbuilt on. So there's a paper claiming if you look at areas that are something like 1.5 to 3 hours commute out from the city center, previously no one would really live in that and commute into the center because this is too far. If you're only going in twice a week, say, that's now within space. And apparently around a lot of big US cities, that stuff is vacant. So I don't know, is that part of elasticity or is that like?
Absolutely. That's exactly what we sort of are expecting and hoping
It's like
find.
fringe Houston and fringe LA and these areas that are just so far from.
That's exactly right. So a lot of the change in population is from CBDs to sort of fringe part of cities. We expected very rural areas would see population increases, but that's actually not true at all. And what determines the covariance between elasticity and demand is really the change from CBDs to exurbs. So exactly what you're talking about. And that's driving all of the results. The sort of rural areas effect is not nearly as important as I expected it to be going in. It turns out it doesn't really matter very much at all.
So one thought was, as workers move towards these new areas and the schools become better and the services around those areas become better, would the elasticity parameters endogenously change in these new places over time? Because you are assuming the same parameters over the two periods, correct?
I think that's very possible. One of our referees made a similar comment. And so our appendix C endogenizes the elasticities. Ultimately, what we learned from endogenizing the elasticities is we're talking about maybe 5% of people moving here. So we don't think it's so big that, it'll affect the elasticities that much. The elasticity estimates from SIEPR and from Baumsnow and Hahn are a function of density. And so you would think that exactly what you're talking about happens. As the density changes, mechanically, the elasticity will change.
So what you showed us are rents, right?
Yes.
Okay. So if I take your model seriously, and I think I can use it to back out, well, I have to make it another assumption. The adjustment from the short run equilibrium to the long run equilibrium happens at a constant pace.
Yes.
If I take that assumption and combine it with your model, I think you can back out an implied time to the long run equilibrium with a simple asset pricing formula. So you gotta set a discount rate and so on, but you can do this city by city, right? There's got to be you take an asset pricing formula.
Yep.
And combine it with your model and this constant adjustment pace assumption. There's only going to be one value of the time it takes to get from the short run to the long run for each city that will be consistent with those equations.
Oh, I see.
So
yeah,
it would be useful to do that. I mean, there's going to be, the discounting, the asset pricing model is, that's going to matter. But the variation across cities will presumably be similar across a wide range of different assumptions you might make for the different asset pricing formulas.
That's interesting. So what we did was assume that all cities will happen at the same rate and then calculate the implied discount rate, which is a little bit of a different
That's kind of
exercise.
the inverse of what
Right,
I'm saying.
exactly. What we did is the inverse
But
exercise.
It seems like you want that the asset pricing ought to be uniform across cities. And then it might tell us something interesting about what the market is expecting the adjustment period to be city by city, which is also interesting.
That's a very interesting exercise. That's a great idea. Thank you. Yeah. Oh, sorry.
So I had kind of two small questions.
Perfect.
Okay, so my first question relates to Nick's in that I'm assuming you're looking at the county level because of data restrictions.
Yes.
But that should change over time and hopefully over the lifetime of the projected project. And I feel like it's important to try to get a little bit smaller than that because of how much of the moves are within city. And so I'm really concerned that you're sort of underestimating the scale of the effects that you're interested in because of the county restriction. The second thing is I think that it'd be nice to say something about the interaction with the commercial real estate market here because they're both like, we're talking about the conversions that are happening downtown and we're talking about retail going to the suburbs. Like there's not, these land markets and real estate markets don't happen in isolation here in this process. And so I don't know how to think about the interaction with the commercial real estate in the simple setting that you're trying to set up.
Those are both great comments. I think I suspect that as you look at finer levels of granularity, you'll see the same pattern of people moving to more elastic places sort of happening over and over again, especially if you look at something like LA County, which is giant. I think that'll be future work, but it's definitely future work we want to do because there's no reason the model has to be at this level. So that's a great suggestion. And oh, right, your other suggestion was about commercial real estate, which I totally agree. This is sort of a side of the things which we've totally ignored, but I think is probably really important. Yeah. Thank you.
All right, thanks so much. Great, so final paper of the session presented by Charly Porcher is on remote work and city structure.
Thank you very much to the organizers for including the paper in the program. This is joint work with Ferdinando Monte and Esteban Rossi-Hansberg. So I'm conscious I'm the last barrier between you and dinner, so I'm going to try to remain as entertaining as I can. We're all here to discuss the consequences of the recent dramatic adoption of remote work. And what we do in this paper is that we want to reflect on one of the possible long-run consequences of remote work on the structure of cities. And at the heart of what we're going to think about is one of the most central ideas in urban economics, which is that people benefit from being close to each other, right? If you go to the city center, you benefit because you meet other people, right? And what remote work changes is that it allows us to live in the same city without being in the same place when we produce, right? And that could mean that we might lose on these interactions. And this idea leads to a coordination problem, right? I benefit from going to downtown areas if others do, but if others don't, then I benefit less, and maybe I decide to also stay home, right? And this coordination problem could lead to multiple stable equilibria at the level of a city, with one featuring high levels of commuting or one featuring low levels of commuting, right? And as we know, when we are in context, when we think about context with potential multiple equilibria, initial conditions matter, right? And this is where the pandemic lockdowns come into the picture, right? The lockdowns moved us and forced us to move to an initial situation where we're not commuting. And if we lived in a city that could sustain these low levels of commuting, then it might have remained at these levels and not have returned to higher levels of commuting. And so what I'm going to show you as one of our main empirical results is that we see very heterogeneous patterns if we look at different cities in terms of activities in the city centers throughout the pandemic and the recovery. And if we think about visits to city centers, in some cities, particularly smaller cities, we'll find that they have mostly returned to their pre-pandemic levels. But in the larger cities, we see that they remain much below pre-pandemic levels. And so we're going to argue that if we think about the responses of these cities through the lens of this coordination problem, we can predict pretty well which are the cities that came back and which are the ones that didn't, depending on whether we think they could sustain these low levels of commuting in the first place. Another consequence of thinking about remote work through this coordination problem is that it has implications for the strength of agglomeration forces in a city, and therefore it has implications for aggregate productivity and ultimately for how welfare is affected by whether a city has switched or not to these low levels of commuting. So what we're going to do in the paper is first, it's try to think conceptually, right, about this question of coordination problem. And so we're going to build what we think is the simplest model that can capture this idea of remote work in a city with the key trade-offs at play, and that can help us understand what would determine how a city responds to the types of lockdown shocks that we were talking about when the decision of whether to be remote is endogenous. And so we're going to consider a monocentric city model in which all firms are located in the center, in the CBD, and people are going to live in one unit of housing. So you'll see a lot of the characteristics of the model are simplified to their most so that we can capture the role of this coordination problem. And so people can decide whether they want to deliver work remotely or in person. If they work in person, they have to commute to the city center, right? And if they work from home, they can stay some fraction of the week at home. And wages are going to be a function of the productivity. They're going to vary by the delivery mode. They're going to be, reflecting the fact that the productivity of work in the office or at home might be different. And the key trade-offs that people are going to face is that remote work offers some attractive features. It offers lower commuting costs, potentially lower rents if people move to the outskirts of the city, also higher amenities from spending more time at home. And so as I say this, I'm kind of thinking of all the papers that we've talked about that kind of fit into these different important aspects. But that comes at potentially the expense of lower wages and lower downtown amenities. Okay. And so just one slide to highlight the critical elements of the model. We're going to think that office work, the productivity of one efficiency unit of work in the office is A, but it's Z at home, and this could be potentially different. The number of efficiency units that people can provide is going to depend on the number of in-person interactions that people have, right? With some elasticity delta. So this delta here is going to be an agglomeration force in the sense of an urban model. And so I'm going to depict in blue everything that's an agglomeration force, and in red, everything that's a congestion force. And so if you're a remote worker, we're going to say that you can spend a fraction that's fixed, a fraction mu of the time at home. And so for the LC, the number of people who decide to be commuters, they're going to receive a wage that's going to be the baseline productivity of office work multiplied by the number of efficiency units that they can provide. And that number of efficiency units is going to be a function of basically the typical number of people that are present in the office. So taking into account full-time commuters and part-time commuters. And the remote workers, if they choose to be remote, we're going to index them by M for mixed, right? They have this kind of part-time commuting allocation. Their wage is going to reflect that, with being the average between office wage, and at-home wage. So now this is going to be a dynamic model. And so people are going to make decisions every period about whether they want to readjust their labor delivery mode. But even within period, right, people are making some choices. Some of them, so the choices they make is where do they want to live in the city, how far from the city center, and how much they want to consume in terms of housing and goods. So if we think, for example, here about the remote workers that I'm calling M here, there's a Cobb-Douglas form of their utility in consumption of housing and goods. But the more, I think, interesting part here is what happens to their utility coming from being at home. And so for a fraction of the week, they enjoy this amenity from being at home. And then the rest of the time, they enjoy part of the amenities from being downtown. Part of these amenities might be increasing in the number of people that come to downtown, right? So if I'm more likely to have lunch with my friends, the more people come to the city center. That could be a positive externality here, but there's a cost to going to the office. Particularly, there's a transportation cost that will increase with the distance between your home and the city center, with some elasticity gamma, and then potentially some congestion in the form of higher traffic with more people commuting, right? And so this kind of what we're going to find ultimately is that we're not going to be able to reject in the data that the net effect from these amenities versus congestion is different from zero. So really the key elasticities that will matter for what we have to say today will be delta and gamma, this distance elasticity of transportation costs. If we want to think about commuters, we just replace mu by zero in this equation and we get what is their flow of utility. So then the next step is thinking about how people readjust every period their choices, and they're going to weigh these flow utilities between remote work and in-person work, with also idiosyncratic preference shocks that they're going to draw every period in a very typical discrete choice model style, subject to fixed switching costs. Okay, so what this gives us, right, is an economy that will be governed by one key state variable, which will be the number of commuters at a given point in time. And that variable is going to evolve over time and lead the city to converge eventually to a stationary equilibrium that I'm going to characterize now. And so this is really the advantage of having this kind of simplicity, that we can characterize the city through this only state variable. And the key result from this analysis, I'm going to summarize in this graph here that that tells us under which condition does a city potentially feature this multiple equilibria, this multiple stable equilibria. And so what we see is the different regions, depending on what determines whether a city can have multiple equilibria, depending on the strength of their agglomeration forces on the x-axis, and the productivity of remote work, z, relative to office work, a, right? And so what we find is that if the agglomeration forces are too weak, then there is a unique equilibrium. But if they're strong enough, and if the relative productivity of remote work is kind of in a medium range, so that it's not too low so that no one wants to do remote work, it's not too high so that everyone wants to do remote work. If it's kind of in this between zone, then we get multiplicity in the form of this kind of cone of multiplicity, okay? And so the next step really is for us to see the parallel on how to understand, how to apply this concept to the data and see if this simple theory, once we try to get some numbers on these key parameters, whether it helps us understand what we see in the data, okay? So let me just fix ideas by one example before I move to the data. It's just considering a city with low agglomeration externality. And this is a phase diagram, so it tells us the number of commuters tomorrow as a function of the number of commuters today. If the agglomeration forces are weak, then the lockdowns, what they do is that they send us all home, so LC goes to 0, and then once we release the lockdowns, the city comes back to its pre-pandemic equilibrium, right? There's no other possibilities for this city. If we have a high agglomeration externality, this is the shape, typical shape of the phase diagram. And so this is where we see that, the lockdown, once released, is going to bring the city back to a different stable equilibrium with low commuting values, okay? And that's really the now the question is, do we see some sort of a parallel to this in the data? So some descriptive evidence that I want to show you. This is now data from cell phone tracking data provided by SafeGraph, where what we do is we count the number of visits to the city center over a year in each block groups in these cities, controlling for variations of a month in the number and also the changes in where people reside, in order to remain consistent. And what we see is, relative to, so everything is expressed relative to January 2020. And we see patterns that, we're pretty familiar with now from different data sets, is that, in April of 2020, there was a drop of about 80% of visits to the city center across the board. So, in all of these 3 example cities here. If we think about New York, we see that there was a partial recovery, but by mid-2022, it was still well below 50% of trips to the city center. And it's a very similar story for San Francisco, right? It looks quite different if we think about Madison, Wisconsin, right? And so this is something that we can see more systematically across cities. If we now divide cities between the large cities, those that have more than 1.5 million employment, and the small cities that have less than 150,000 employment, we see this clear divergence, right? Where the initial drop in the visits to the city center is, between 20 and 30% during the early month of the pandemic, and then the largest cities stabilize around 60% of mobility or visits to the center, whereas the smaller cities are pretty much back. Right? So this is a very big difference, right? It's 40% variation between the large and the small cities. Moving to housing now. So a lot of us have been talking about housing today. So I'm going to go quickly because this is an exercise that has been performed, particularly for big cities. What I'm going to tell you what happens also in small cities with the sample that we can use. But we're going to basically also look at Zillow level data at the zip code level. This is going to be housing prices, just because there's a little bit more coverage of housing prices. And so we're going to estimate the distance gradients, right, with respect to the city center. And I'm plotting here everything relative to January 2020. And I'm also multiplying everything by -1 in order to interpret a decline in this curve as a decline in the relative attractiveness of the city centers. Okay, so we see that in New York, the gradient went down and stayed down, and similarly for San Francisco. And for Madison, maybe there was some drop in the early stages of the pandemic, but by the end of 2022, it was back to pre-pandemic levels. Okay, and again, we can do this systematically across cities, and we find this kind of similar divergence between the cities that have more than 1.5 million employment, the big cities that went down and stayed down in terms of these gradients, and the small cities where things were pretty much back to pre-pandemic levels. Okay, so this seems to we see emerging two broad categories of cities, right? Those that returned to pre-pandemic attractiveness of their city centers in terms of housing prices, in terms of commuting, and those that remain stuck with very low levels of visits to the centers and attractiveness of the city centers in terms of housing. And so the next step for us is, take our data, our model to the data, try to calibrate it and put some numbers into these parameters for different cities and see whether we can explain whether the cities that we see not coming back are those that we predict are more likely to be in that cone of multiplicity, right? That they could be stuck in this coordination equilibrium with low commuting. So for that, we are going to need to turn to the data, and this is where I want to emphasize that this exercise is a way for us to test the predictions of the model, to kind of whether the theory has a bite in the data. But there's a lot of the parameters that we need that collectively, as researchers, we have very little idea about their actual magnitudes. So a lot of work today shows that we have a lot to learn about what determines these different parameters. So nevertheless, we're going to do our best with the data that we have available. And so we're going to turn to the National Longitudinal Survey of Youth and the panel 79. And for that, with that wave, we have information about the number of hours that people report working from home, and we're going to use it to calibrate two key parameters. And we're going to simplify things a little bit. We're going to assume that the switching cost, right, between remote work and in office work is going to be the same across cities, and so will be the elasticity, the dispersion of those preferences, right? And so with the NLSY, the number of hours worked from home that we see in that panel, we're constructing transition probabilities, transition at the individual level into and out of remote work. And for example, the first thing we do is we ask, when the wage differential that we see people getting between in-person work and remote work is larger, by how much do transition into remote work increase, right? And we get an elasticity of about 2. So that's the first set of parameters. And then we need to get everything else. And so all of the other parameters we're going to obtain as city specific. Okay, so they're going to be different for each city that we have in our sample. And we're going to end up with 274 cities at the end. For the agglomeration externality, we're going to use estimates that Esteban Rossi-Hansberg in his previous work has obtained from industry level. And we're going to aggregate them at the level of a city using the industry composition in terms of employment. I guess one of the very tricky parts is, how do we calibrate the relative efficiency of remote work, right? The Z over A. And so for that, we're going to try to leverage the information we have in the NLSY, where we do have variation at the individual level in the number of hours that people spend at home. We see their earnings. And so we estimate occupation-specific remote work penalties or potential premia. and we use those occupation-specific numbers to aggregate them at the city level. And on average, we find about 10% discount for remote work through this method, right? And importantly, it's controlling for persistent and observed heterogeneity between people using the panel dimension of the data. And then the last set of parameters we need is the elasticity of commuting cost to distance. And here, it's going to be pretty standard. We're going to go to the ACS, like get census block group data on the rents, and do a gradient regression to estimate those gammas by city. Okay, so what do we get? Well, we're going to get predictions about which cities fall in that cone, right? Which ones are in that cones? And the question is that prediction about whether a city is in the cone of multiplicity associated with what we see in terms of that drop in commuting or in visits to the city center? And so this is the main test of our results. We see that the cities that had the strongest reduction in trips to the CBD, so you think, San Francisco and New York, are those that we predict are the most likely to be in that cone. And then this is the result from a bin scatter where we fit a probit model to this set of cities. So we see this as pretty encouraging that, yeah, cities that, are pretty much back in terms of commuting, we don't tend to predict that they should be in a multiplicity situation. Okay, now we can also summarize what we find in terms of the share of cities in the cone by employment, right? I showed you this very strong relationship between the patterns of recovery and employment. And so similarly, we find that the biggest cities are more likely to be in that multiplicity potential. Right. And so in a sense, this is telling us that the size of cities is a good summary for the set of parameters of characteristics that make cities more subject to this coordination problem. Okay, so last thing I want to show you is what happens if we push the model, again, with all the caveats that I want, to really clarify that this is really just if we go all the way and ask what are the welfare consequences of these switches to a different equilibrium, right? So this is something we can do if we, for all the cities that are in the cone, for which there are two possible stable equilibria, one with high commuting and one with low commuting, and just ask, omitting for now transitions between these two stations, these two equilibria, just thinking about the stationary equilibria, what is the welfare difference between those two equilibria? And we find some results that are between 0 and 3% decline in welfare. And so, these are not zero, but also not huge, right? But what we learn from this exercise is that we can also decompose what is driving those changes. And we see that there's two competing forces, right? In a city like New York, people are no longer going to the office. And so this is predicting a loss from these interactions, externality that makes people earn higher wages is going down. And in fact, wages would be going down quite a bit. But that's compensated by gains from not having to commute, right? Enjoying those amenities and also the option value of switching into in-person in the future if you desire. And so that's kind of why in the end there's quite a lot of action, but it's kind of a reallocation about where do people get their utility from, right? They tend to benefit now more from spending more time at home and willing to accept these lower wages. And that's kind of the main point of that exercise. So let me conclude. What we do in this paper, right, is that we just entertain this idea that is very central in urban economics, that people should benefit from being close to each other, right? And that's a very essential point if we want to think about cities. And so we take it at face value and we ask, what are the consequences of remote work for the workings of these types of interactions, right? And the crucial consequences is that remote work allows us to remain in the same city, participate in the same housing markets, the same consumption markets, but not necessarily have to interact in person. And that can change, in fact, the way cities could operate, right? And in a sense, could lead to what we see as this coordination problem, where it could have dramatic effects in the number of people who choose to go to the office, and that that new form of multiplicity can only exist if the strength of the remote work technology is productive enough, right? That's what the cones highlighted, that you need that technology to be in the right, exactly the right area. We find in the data, when we take this to the data, clear evidence that there's very heterogeneous patterns in the recovery across cities, and that this theory seems to do quite well in explaining that heterogeneity. Okay, I'm going to stop here. Thank you very much.
Thanks. This is a very interesting and ambitious paper. First, an observation that about the data. The SafeGraph data seem to be telling a somewhat different story about the relationship between the increase in work from home or stickiness and density than we see in the SWAY data. So in the SWAY data across the entire density distribution in the United States, we see higher work from home levels now than what prevailed before the pandemic, which seems to be different than what's coming out from the SafeGraph data. I'm not saying one or the other is right or wrong. I'm just, that's actually a critical thing for the evaluation of your model. I don't know what's the source of that disconnect between the two data sources, but I would get a less favorable assessment for your interpretation, I think, using the SWAY data or the HPS. Well, we haven't looked at the HPS. So that's just an observation, and I don't know.
No, thanks. This is definitely something.
Yeah, it's worth thinking about. Second, they're in your model. There is a region that doesn't appear to show up in the data, as I understand it, which is the set of cities where the agglomeration economies are so strong that even if you hit them with a pandemic shock, you'll bounce back. Okay, that's a feature of isn't that a possible outcome in your model?
You hit them with the lockdown and they bounce back.
And they bounce back to the high agglomeration, high density outcome.
Right. Those are not
the small cities in your model. What I don't understand is why according to your model's interpretation of the data, there aren't some highly dense cities that also bounce back because the agglomeration economies. I just didn't understand. And then the third thing is just another observation. You know, if we take your interpretation of the data seriously, then all we need to do in San Francisco or New York, is force everybody to come back for say a year, long enough to overcome the switching costs that were part of your model, and they'll stick there. And I guess I don't really believe that, but maybe you do. Well, but to be fair to him, you would need a coordination mechanism across businesses, across people that actually makes them come back. So it's not clear how you would engineer that.
Right.
I guess you could do it in DC with federal government employees. That would be the closest.
Right.
So
but yeah, no. So just to respond very briefly. So on the part that you just mentioned. So on the part that you mentioned earlier, right? So why is it that the big cities are those that we think are not coming back? This is really crucial, right? And the idea is the stronger the agglomeration force, the more likely do you have to have this bang bang type of mechanism, right? And so it's really if you think about it through this bang bang kind of situation where, because there's very little frictions to sticking, right? That's why you get a stable environment when the agglomeration forces are strong. Yeah. On the coordination, I agree with you, right? This model has very stark predictions for what happens if you manage to overcome this coordination problem. You know, in a sense, everything goes away. And so that's something that, you know, in the end, if we were to see some examples of, you know, successful coordinated return to the office, that would be a really great test of whether that's a story. And I know that as in DC, there's definitely perhaps the city where there's the strongest momentum to try to do that, but I don't think it's happened yet at all. So we'll see. Thanks.
Yeah, I have a follow-up comment to this discussion, actually. So you also see different results across cities when you look at different geolocation data providers. So like Placer AI is another data source, and they actually argue that New York, for example, has come back much more in person. And actually it's the Sunbelt cities that have a lot of remote workers. Sort of consistent with that, you see MTA traffic really has been coming back in New York City. And if you look at ACS data, you see that New York City actually is not on the top list of remote workers. It's really like Raleigh suburbs, right? Like Atlanta suburbs. Those areas really have a ton of remote workers. So yeah, I know in your model,
But just
you
to
get
clarify
that.
on the data, it's a really important point and something that I was kind of lost in the way I was describing, but we're really looking only at visits to the city center, and a city center is a very narrowly defined area, right? And so in the case of New York City, it's important because if we think about it's mobility to Midtown and the financial district only, right? And so I think there's a lot of mobility that has recovered in the city overall that could be masked by.
But that's exactly what's come back in the latest subway data. Right, it's really traffic to Midtown, the financial district, that is kind of going up. So I think the broader point about equilibria, is kind of well taken. But I think the full story about what regions are actually going to have the most remote work is a little bit more unclear to me. I can actually imagine a future in which there's actually these Sunbelt regions that have very large homes, longer and longer commutes to get to the office that actually wind up having more remote work in the long run. Whereas it's potentially even the large cities, because people have small homes. Might have shorter commutes, if they have a public transit and so forth, might actually come back to the office greater amount. So I think the full story is yet to be written. And I think it's worth comparing different data providers that might result in different conclusions about how many people are coming back even to the urban cores.
Thank you.